Hello everyone. Today I'll show the solutions to problems 5 and 6 of round 170 of the Prairie Math League. For problem number 5, we wish to find the hundreds digit of 2 to the 2011 to the power of 2011. Now, first of all, I would like to point out that if we're dealing with hundreds digit, no matter how many times we multiply 2011, this 2000 is not going to matter at all, because at any point when we multiply by 2000, we're already going beyond the hundreds digit. So we can ignore that. And the hundreds digit is just going to be, in fact, the last 3 digits will just be the same as 11 to the 2011. Now, in fact, we can just consider the last 3 digits, and this makes things easier. So we consider 11 to the 2011 mod 1000. This is basically saying that we care about what the last 3 digits are. And we're going to use Euler's-Toshin theorem for this. If a and m are positive integers, then a to the power of the Toshin function of m is equal to congruent to 1 mod m, where the Toshin function is a number of relatively prime numbers smaller than m that is given by the formula here. Now, this is the prime factorization. So notice that for m equals 1000 in this case, we must have the primes 2 and 5. So Toshin of 1000 is equal to 1 over... m times 1 over 2 times 4 over 5, which is equal to 400. Now notice that this means that 11 to the 400 is congruent to 1 mod 1000. Therefore, 11 to the power of 2000 is also congruent to 1 mod 1000. Then this implies that 11 to the 2011 is congruent to 11 to the 2000 times 11 to the power of 11, which is congruent to 11 to the power of 11, because this is 1. And the same thing for this. So now we just need to find this, and this is just arithmetic. But notice that we can make things simpler if we just consider 11 times 11 to the power of 5, 11 to the power of 5 squared, which is congruent to 11 times 51 squared mod 1000, which is congruent to 611 mod 1000. And the hundreds digit is 6, so our answer is 6. Now, for the next problem, we have a cube that is a 2 by 2 cubed, 2 by 2 by 2 cube that is constructed from 4 white cubes and 4 blue cubes, and we wish to find the number of ways to construct such a cube, where we consider rotations to be the same. Now, the way we're going to approach this kind of problem is by doing casework. So we're going to focus specifically on the bottom face, the bottom 4 cubes, these ones. Now, to start, we know that if we're going to be drawing these tangent diagrams, we probably won't be seeing what's going on. So we're going to draw something like this instead. So anyways, case 1 is 4 blue cubes on the bottom. And in this case, we mark these as blue dots. And obviously, there's only one configuration. So this gives us 1 way in total. Now, case 2 is 3 blue cubes. And these 4 solutions can all be shown to be unique. Notice that even though these two do look similar, they are subtly different, because you can reflect them to get one or the other, but you can't rotate them. So, or I don't know about the reflection part, but you definitely can't you can't rotate one to get the other. So these are all actually unique configurations. And if you want to identify these, one kind of looks like this, a corner. One is like a corner staircase. And the other two are just like these kind of shapes. Now we go on to the 2 blue cubes on the bottom. There are 6 ways to, if we have 2 blue cubes at the bottom, we can either have them sharing a side, or we can have them like diagonally across. And once we fix these to like a certain edge or diagonal respectively, there are 6 ways to arrange the remaining 2 cubes. So yeah, 6 ways. And out of all of these, notice that a lot of these are duplicates of the previous case, because if they have 4 or 3 cubes on a face, then we can just rotate them to get the previous 2 cases. So we can eliminate this case, this case, this case, this case, and this case, and this gives us 1 new case. If we go to the other side, where the diagonals are separated, we can eliminate this case. Hang on. This case, and this leaves us with three cases. No, wait, this is also not a case. So this leaves us with two more cases. Now, this is just a duplicate of this case, so we can cross this out. But this gives us one final case. So, out of all of these, this gives 4, this gives 1, and this gives 2 more. Finally, if there's less than one's less than or equal to 1 blue cubes on the bottom, then there therefore must be equal to three or more blue cubes on the top, which basically allows us to instantly rotate the cube 180 to reduce to these two cases. So this case doesn't exist, and therefore the answer is the sum of these three numbers, or 7, which is option choice A. And we're done. Thank you for watching.